Good afternoon, AP Physics. Sorry it's been a while since I've made a video. Today I want to show you how to solve problems that involve inclined planes and ramps. This is some of the most challenging work that we'll do because of this angle right here. And so tomorrow in class we're really going to do a formal lesson about this, but for today I wanted to give you guys kind of some pre-exposure to what we're going to be talking about tomorrow. So our situation here is we have this box of mass m that's sitting on a ramp. And in physics, we love ramps. A ramp is just any surface that isn't perfectly flat. So it could be tilted up, like this one here, or you could have a ramp that's tilted down, which we could see in the future. And so in order to begin to solve these problems, the best strategy is to draw a free body diagram for the mass. Okay? Now, the big thing to note, just because the mass is sitting on a ramp doesn't mean the force of gravity does anything special. Like we've said since the beginning of the year, the force of gravity always pulls straight down on an object. So for this mass right here, the force of gravity pulls straight down on it. Okay? Now, the other thing to note is that this is a frictionless ramp, so we don't have to worry about friction here. But we do need to think about what other forces are acting on the object. One of the big things that I've noticed we've forgotten in class is that to determine the forces to add here, you need to think about what's pushing or pulling on the box. So we know Earth is pulling on the box. There's nothing else around it up here, but there is this surface that's pushing on it. Now the important thing to know is that with ramps, with normal forces, they're always perpendicular to the surface. So if we think about when we would have a flat table, and we would put a box on it, the normal force always pointed straight up. Or just last week we saw that if you held something up against the wall, the normal force pointed exactly opposite the wall. And so if you're a ramp, again, that normal force is going to point exactly opposite of the ramp. And this is where that angle comes into play. Okay? So FG still points straight down, but the normal force points at an angle. So to answer question C, we would say the normal force acts on the mass at an angle. Okay? Next, we want to look at what force is causing the mass to accelerate. Okay? Now this is where things get to be a little bit more tricky. And so we're going to have to apply a little bit of physics knowledge or intuition here to think about this object. Okay? So if we imagine just putting something on a ramp, and there's no friction here, so this is a perfectly smooth ramp. If I were to put something on top of it, think to yourself, which way would it move? Hopefully you thought to yourself that it's going to move down the ramp this way. Okay? Now, that means then that there's kind of this invisible motion. This is clearly not a free body diagram, but I'm showing velocity right here. Okay? The velocity is going to go this way. Well, we could think of this then as one component of motion, and this would be another component of the motion. And these two are at 90 degrees. And so what do we know about vertical and horizontal components? They don't affect each other. So this normal force is not actually causing the box to accelerate. Instead then, it's this gravitational force that's causing the mass to accelerate. So for D, the Fg, force of gravity, or the force from Earth, causes the mass to accelerate. While the ramp does not. Okay. So now, since we've revisited friction today, let's apply it to a ramp problem. This is much more realistic. So now we have a mass sitting on the ramp, but there is a non-negligible force of friction. Non-negligible means there is friction. Okay? In this case, non-negligible just means that you have to account for it. The important thing to note here is that the mass remains at rest when placed on the ramp. So let's draw a free body for this. I'm going to draw kind of a rough sketch over here. Force of gravity pulls straight down. the normal force is going to go exactly opposite of the ramp. We know that the velocity is going to go this way. And so if it's going to move this way, that means that there has to be this friction force that points opposite the velocity. One of our rules of friction is that it's always opposite motion. And so, like we talked about in the problem above, the velocity and the force are at a right angle. And if the force of friction opposes the velocity, these two must also be at a right angle. So when we apply this to our free body diagram, we've got this Fg down here. We've got this normal force coming up at an angle. And then we have this force of friction that's 90 degrees to that. Okay? Now, what we're going to talk about tomorrow is how then do you do some math with this by breaking this down into different components using theta or other angles. But for tonight, just know that you're going to have some angled forces on your ramp, and you're going to have some perpendicular forces. Okay? Hope you guys have a good rest of your night. If you have any questions, please post them on Google Classroom. Bye-bye.